Good afternoon. For me, a civil engineer by degree and a pipeline engineer by profession, it's an honor to be here and presenting in front of you all naval architects. My knowledge in naval architecture is limited to a book, Naval Architecture for Non-Naval Architects, given to me by my naval architect colleague Yesudas in 1997. This presentation is just an overview of subsea pipeline engineering. Many topics are just touched upon, so any questions, please feel free to ask. In this short presentation, we'll discuss about history of offshore pipeline construction, present offshore field architecture, offshore pipelines, design, construction to decommissioning, and at the end, we'll have a Q&A session. So let's start with history. It's quite an interesting story. We all know about D-Day landing at Normandy by Allied forces towards the end of the Second World War. When the planning started, Allied forces knew that after a successful landing, to move forward, they would need gas. So Project PLUTO, pipeline under the ocean, was taken up. Two lines, Bambi and Tambo, were installed by relay across the English Channel. Interested people can watch a BBC documentary and details of the project online. This is called the first offshore pipeline project in the history of the world. Certainly very interesting story. With time and development of new technology by industry leaders such as McDermott, Saipem, Equinix, Subsea7, Allseas, etc., offshore pipeline moved from shallow water to deeper and deeper into the ocean. And presently, we are almost at 10,000 feet water depth. Cross-country pipelines are transporting oil and gas in different parts of the world. For example, Blue Stream, Russia to Turkey across Black Sea, around 400 kilometers subsea. Nord Stream, Russia to Germany along the length of the Baltic Sea, around 1200 kilometers. Planning and execution is on for South Stream, Russia to Europe across Black Sea. Also from my childhood days in India, I grew up hearing about Iran-India or Oman-India pipeline and also Myanmar-India pipeline. These projects have different challenges, political and technology-wise. And I hope someday in future, these may be a reality. In this section, we will see graphical representation of offshore field architecture in the current era. This image represents how we transport hydrocarbon from subsea wellhead to offshore host, a fixed platform or some floating structures. From individual wells, hydrocarbon is transported to a subsea manifold, and from manifold to a fixed or floating structure by pipeline and riser system. We also install umbilicals for subsea control system. Based on the safety philosophy, pipelines are normally controlled by subsea intervention valves, which can isolate pipeline and a fixed or floating system in case of any incident. This image represents how we transport hydrocarbon from offshore host, a fixed platform or a floating structure, to onshore facilities, maybe a refinery or any other facility to store hydrocarbon. From offshore hosts, hydrocarbon is transported to onshore facility by pipeline system that comes from deeper water to a landfall point and then continues onshore. Offshore and onshore parts are isolated by isolation valves at offshore end as well as at onshore end. This image represents how we transport hydrocarbon from subsea wellhead to onshore facilities. From individual wells, hydrocarbon is transported to a subsea manifold by well jumpers, and from subsea manifold, hydrocarbon is transported to onshore facilities by pipeline system that comes from deeper water to a landfall point and then continues onshore. Offshore and onshore ends are isolated using isolation valves. So any incident at one end, we can isolate the other part. This image illustrates FPSO and SCRs. In deeper water, we do not install a separate fixed riser. Instead, pipeline end is simply lifted and connected to FPSO, and the long span of pipeline behaves as a catenary. Shell had developed this technology in the Gulf of Mexico and also has used this in West African deepwater fields. This image illustrates flexible riser system used in deepwater fields. It's a different configuration than SCRs. Flexible riser system has different configuration as well. It primarily forms an S shape. There are different terminologies we use as lazy S, steep S, lazy wave, or steep wave risers. Now let's talk about pipelines, design and construction philosophies. Let's first try to understand why we need a pipeline. Any pipeline operator needs to transport hydrocarbon from point A to point B. We need to do it safely. We need reliability and availability of the system with reduced or no downtime. We need sustainability for its design life of 25 to 30 years, whatever it is. And of course, we need cost optimization. Pipeline system ideally should be much cheaper than transporting oil and gas by tankers. The system design philosophy involves HSE risks as well as asset and business risks. Let's now try to understand the phases in the life cycle, which we normally call cradle to grave. Life cycle starts with the feasibility and concept phase of a project. Once the technological concept and commercial feasibility is established, a project moves to select and execute phase: engineering, fabrication, transportation, installation, and decommissioning. Operate phase starts from commissioning and runs through the design life of the system. These days, reassessment and life extension is quite largely in practice, as marginal fields nearby often try to use existing infrastructure to reduce capex. By using a nearby platform and existing export pipelines, for this structural integrity assessment of pipeline infrastructure towards the end of design life, inspection of effects of corrosion, cathodic protection system are examined to allow operation of the pipeline system beyond its original design life and for some new service conditions. Once the pipeline is no more needed, it is decommissioned by removing the pipeline from the sea or by abandoning by trenching and burial of the pipeline after making it hydrocarbon free. Pipeline design uses two different philosophies: working stress design method and limit state design method. In working stress design method, where SMYS is multiplied by a factor of safety, which is less than 1, to define allowable stresses in the system. Factor of safety differ from code to code. We have BS codes, ISO, ASME, Dutch code, Canadian code, Australian code, and most popular DNV standard. Limit state design method was brought into pipeline industry by DNV in 1996, which was later changed to DNV OSF 101, popularly known as DNV 2000 standard. API RP 1111 also provides limit state guidelines. This is based on risk and reliability, safety class and partial safety factors. This method is also known as LRFD, load and resistance factor design, where load and resistance is compared using partial safety factors. I'm sure all of you are familiar with the left side picture of consequence and likelihood, green, yellow, and red color codes. In summary, we need to keep the snake inside a box, like in the second picture. We cannot change the consequence if things go wrong. But by good engineering practice, we can always try to reduce the likelihood of the snake coming out of the box, which in a way we can say that for the event happening. This is something I believe is very familiar in our lives. I personally used to be confused with these terms till I worked for Lloyd's Register with DOD. In terms of pipeline projects, Plus Society does verification of initial stages of the project, like design or installation. For a certification project, line-wide production at steel mills, design, welding, and installation and pre-commissioning are witnessed and reviewed by the Class Society. Operational integrity assessment and life extension are also done by the Class Society. Certain components of the pipeline system, for example, flexible pipeline, different types of valves or connectors, are also given type approval by Class Society. Normally have two types of pipes: rigid carbon steel pipes with anti-corrosion coating of FBE or polypropylene or polyethylene, and concrete coating to provide on-bottom stability. And we also have flexible pipes, which normally used for deep-water riser system. We also use piping pipe system where a bunch of smaller diameter pipes can be bundled into one large casing pipe, or for certain cases where insulation is required to transport gas and we cannot allow temperature drop to avoid wax formation. A key design aspect of pipeline is presented in the following slides. PB by 2T, hook stress. That's the only formula I have put in this entire presentation. First step of pipeline design is hook stress, hydrocarbon containment. Then we check hydrostatic collapse, very critical for deep water pipelines during installation. Empty pipeline with no pressure inside and external hydrostatic pressure. Buckle propagation is another critical aspect of pipeline design. particularly in deep water. Local failure can run along the length of the pipeline like jet fire. We use thicker sections of pipe as buckle arrestor for deeper water pipelines. Local buckling is critical during installation in layouts and also in case of subsea spans. Stability. This is a very familiar term to naval architects. Our case in pipeline engineering is to make pipe stable on the seabed against hydrodynamic forces by increasing weight of the pipeline and thus increasing frictional resistance. Concrete coating provides weight and reduces buoyancy and thus makes pipe vertically stable and laterally stable. Span analysis is a very critical aspect of pipeline design. Spans occur due to uneven seabed scouring for an operational pipeline, and also local imperfection, as we can see in the last picture. DL guideline provides a detailed analysis method for such spans. Where fatigue limit state is assessed for vortex-induced vibration and direct wave loads. And ultimate limit state is assessed for static bending, VIV, wave loads, pressure effects, axial forces, and also for certain cases, troll gear interference from fishing boats. Thermal expansion and inserted buckling are critical phenomenon for a pipeline design. Heated pipeline wants to expand and soil resistance provides opposite direction force. Therefore, for a pipeline up to certain length, these two forces keep pipeline in equilibrium. We call this a restraint zone with virtual anchors at both ends of the restraint zone. Beyond that, at both ends, pipeline expands, and end expansion spool, a L or Z shaped, is designed to mitigate the effect. In the restraint zone, pipeline has huge amount of force in the wall. Therefore, due to any imperfection or out of straightness, pipeline may buckle. The buried pipeline may buckle vertically and come out of the barrier, while a pipeline in the seabed can laterally buckle and move sideways. Rock dumping is a popular method to mitigate lateral or apical buckling. This image shows expansion spool and riser arrangement for fixed platforms. We have already discussed about the expansion spool in the previous slide. Risers are normally connected by guide clamps to the jacket legs, allowing thermal expansion in the vertical plane. In the next few slides, we'll discuss about the design aspects of riser system. Risers are designed against yielding, buckling, and fatigue failure. Loads include wet loads, which are riser material, coatings, anode, flanges, transported fluids, marine growth, buoyancy. Pressure loads include internal design pressure. Thermal loads include design temperature, expansion load, and environmental loads include hydrodynamic loads, wind loads, ice load, and seismic load. Spool and riser system also needs protection from ship impact. So we put it preferably close to a jacket leg and provide ship and boat fender or a riser guard. It also needs protection from dropped object from platform or supply boats and protection from snagging by fishing boats. This picture is of a flexible pipeline failure in West Africa. Restored fish got stuck in a pipeline. We have now reached the installation stage. In the top slide, J-lay method is shown. The shape looks like a J in deeper water where the ramp is vertical. S-lay is the most conventional method for shallow water pipeline installation. It also is used in deep water with high tension capacity vessels. Relay is quite popular in the North Sea, where pipe string is welded in an onshore facility and reel in a relay barge. This is used for seamless pipes and installed in a specialized vessel with a reel and a straightener. Tow installation is used for short lengths of pipeline or for shore approaches where pipeline by using buoyancy modules are made to float on the surface or mid-depth or on bottom. Risers are installed by stop-on method and secured by riser clamps connected with jacket legs. In some cases, jacket comes with pre-installed risers. We are almost towards the end of the presentation and we'll talk about decommissioning now. Firstly, pipeline needs to be made hydrocarbon free. For buried pipelines, minor corrective measures are required so that the pipeline are not exposed in the long term. For pipelines on seabed, major corrective measures are required to trench and bury the pipeline. In case of leaving the pipeline under seabed is not feasible, pipelines have to be cut in small pieces and removed, or reverse process of pipe lay can be performed and pipeline can be recovered to a lay barge and cut into small pieces and taken back to shore for reuse or scrapping. Till COVID-19 and low oil price changed the offshore project world, industry was going deeper and deeper. High pressure, high temperature field development, Arctic exploration was on the cards. Feasibility of these are questionable at this moment. Also, the world is moving towards greener energy. More and more offshore wind, offshore solar, offshore hydrogen projects are coming up in the horizon. So future looks very interesting. Now it's time for your questions. I love Builder. Thank you very much for your time and please stay safe and please maintain social distancing.